How do mathematicians build massive, intricate algebraic structures? They don't start from scratch. They take simple, well-understood pieces and snap them together. Before we look at how they connect, let's establish our pieces. We are dealing strictly with abelian groups. In this environment, the group operation is always addition. The identity element is 0, and the order of elements never matters. A plus B equals B plus A. If we take two of these groups, say G and H, we can stack them side by side to create a composite structure. This combined group is the direct sum, written as G O plus H. By running operations in parallel, this mechanism gives us a way to assemble highly organized, multidimensional structures while perfectly preserving the rules of the original groups inside. Let's formalize the math. If we have a finite number of groups, we string them together using the direct sum notation. G1 direct sum G2 all the way to Gn. Inside this new combined group, the elements act like coordinates. To add two elements, you simply add their corresponding coordinates together. First position with first position, second with second. Let's do an actual calculation using the integers modulo 2 and modulo 3. If we add the element 1, 2 to the element 1, 1, we apply the individual group rules to each slot. 1 plus 1 in mod 2 is 0. 2 plus 1 in mod 3 is also 0. So our final coordinate is 0, 0. As long as the number of groups is finite, the direct sum is just an exercise in parallel arithmetic. There is no crosstalk between the coordinates. The math gets far more strict when we scale up. What happens if we have an infinite index of groups, denoted as G alpha? This text defines the Cartesian product of an indexed family of sets. In topology, an infinite Cartesian product allows an element to have non-zero values stretching out forever across its coordinates. The direct sum plays by a tighter rule. If you construct an infinite tuple, that tuple is only a valid element in the direct sum if all but a finite number of its coordinates are exactly 0. We call this property having finite support. You can have non-zero elements at the beginning, but eventually the tuple must flatline into an endless string of zeros. Let's test this rule. If we take the direct sum of infinitely many copies of the integers, is the infinite sequence of ones a valid member of that group? The answer is no. Because the ones never stop, the sequence fails the rule of finite support. This single restriction is the exact boundary that separates the direct sum from the direct product when dealing with infinite groups. Now we can map how functions behave in this space. The universal property, or the extension theorem, explains how outside mappings interact with the direct sum. We start with our individual groups on the left and a target abelian group, H, on the right. Suppose we find a valid homomorphism, a structure-preserving map, from each individual starting group into H. The theorem states that if those individual maps exist, they inevitably stitch together into exactly one unique, overarching homomorphism from the entire direct sum into that target group. By ensuring every component maps correctly, the direct sum acts as a perfect mathematical bridge, unifying these individual mappings into a single structured whole. Let's consolidate. First, direct sums align tuples and execute strict component-wise addition. Second, infinite collections must have finite support, ending in zeros. Third, mapping each original group uniquely maps the entire direct sum into that target space. If this breakdown clarified the algebra, leave a like and subscribe. We visualize dense mathematical concepts